Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we review first principles, which is the basic idea of calculus. So let's say we've got some weird random looking function like this. So sometimes we need to calculate its rate of change or its gradient. But this would be very complicated for a function like this because unfortunately the rate of change is itself changing. The function is changing differently in this area than it is in this area. Here the function's increasing, here it's decreasing, and then it's increasing again. In fact, this function is changing at a different rate at every single point along the curve. The gradient is different at every single point on this curve. So how can we find a way to calculate the gradient of this function at a given point? So let's say I want to calculate the gradient at this point here. So I'm just going to call x the x value of this point. What I actually need to do is place a second point on this curve and calculate the gradient of the line that passes through those 2 points. So let's make the second point here. It could be anywhere. What I'm going to do is I'm going to let h be the distance along the x-axis between these 2 points. So if the first point was x, the second x value will be x plus h because the distance between them I've set to h. So for the y values, I'm just going to call this y value here f of x, f of whatever the x value was, and then the y value at this point will be f of x plus h. So to calculate the gradient of the blue curve at the red point, I'm actually going to calculate the gradient of this line that goes through the red and the green points. So the gradient of a line is calculated using the 2-point formula. So it's y2 minus y1 over x2 minus x1. But of course, we can make the bottom easier to work with, so x plus h minus x is just h. So this is what we have from the 2-point formula. But the point is, we now have to look at, well, what about the distance between the 2 points? I mean, if we want to know the gradient here, why did we pick the second point up here? We could just as easily have picked, say, the second point over here and calculated the gradient of this line. You can see that the yellow line, though, it is not a good indication of the gradient at this point. The yellow line's not even going in the same direction as the blue curve at this particular point. The black line is going in the same direction, but it's not 100% accurate. What we want is we want the 2 points to be infinitesimally close together. Then we use the 2-point formula for 2 points that are so close together, it will give a very good indication of the gradient at this particular point. So what we want to do is minimize the distance between the 2 points. Now the distance on the x-axis between the 2 points was h, so we want that to be as small as possible, and mathematically we write it like this: the limit as h approaches 0. So this here gives us the first derivative, which is f dash x. It is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So let's look at some examples where we'll actually use this formula. So this is the formula we just derived on the previous slide. We're going to use this first principles formula to differentiate the function x cubed minus x. So we're going to find f dash of x. So to start with, what we need to do, we know fx, we need to know f of x plus h. So I'm going to take this formula and everywhere we see an x, replace it with x plus h. So in order to use this formula up here, we're going to need to expand these brackets. So to expand these brackets, we need Pascal's triangle. We're doing a binomial expansion. So to do the binomial expansion, we're going to start with the highest power of x, x to the power of 3, and with each subsequent term, we're going to decrease the power of x by 1 each time. So this is just so far doing x plus h all cubed. Now we start the opposite with h. So it's going to start at this end, h cubed, and again, we're going to decrease the power of h each time by 1. So h squared, h to the power of 1, and this will be h to the power of 0. So all of these terms get added together. So Pascal's triangle, remember, tells us the coefficient of each of these terms. So because it's to the power of 3, we need to go to the third row of Pascal's triangle, which is 1, 3, 3, 1. So they're the coefficients. 1, 3, 3, 1. And we're going to make it a bit easier on ourselves. Of course, we don't need to write the 1s. We don't need to write h to the power of 0 or x to the power of 0 because they're both 1. So this here is the expansion of x plus h cubed. And then we've got this part here, minus x plus h. We can't forget that. So the minus just goes to each term. So it becomes minus x minus h. So this, all of this long complicated expression is f of x plus h, what I'm going to substitute here. So the derivative is going to be the limit as h approaches 0 of f of x plus h, so this long expression here, minus f of x, so we're going to minus that part here, so that gets minus x cubed, and then we go minus x, obviously becomes positive x, so that's the top, and then on the bottom, it's always just h. So what we're going to do now is simplify the top. We've got x cubed here, minus x cubed here. So we may as well just rub them out. Similarly, here we have an x minus x plus x. So after you've simplified the top, every one of the terms should have a h in, or you've done something wrong. This is just when we're differentiating polynomials. So see, all of these terms here have a h. So what we're now going to do is divide each term by h. We're going to divide this by h, this by h, this by h, and this by h. And this is what we end up with. So now our final step is to actually take the limit as h approaches 0. So as h approaches 0, this becomes 0 because you're timesing by 0. This becomes 0, and you're left with 3x squared minus 1. So that is the derivative of our original function x cubed minus x. So this derivative here is a function itself. When you differentiate this function, we got another function. This is the gradient function, and you substitute in values of x, and it will tell you the gradient at that point. So for example, f dash of 2, which means the first derivative evaluated at 2, if I substitute 2 into this formula here, I get 3 times 2 squared minus 1, that gives me 11. So when x equals 2, at the point on this curve where x equals 2, the gradient would be 11. This is just a function that tells us how to find the gradient of this function at different x values. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.